So today we have the pleasure of having two very wonderful speakers. Our main speaker is Professor Jeff Potoff, who is a department chair and professor of chemical engineering and material science at Wayne State University. Jeff obtained his bachelor's degree at MSU. Then he went to Cornell to do a master's and PhD with Errington Panagiotopoulos, who was at Cornell at the time. And after that, he did a postdoc with Ilya Sipman at University of Minnesota before starting his own group at Wayne State. And one of the things that I really enjoy about Jeff's work is his interest, focus, and obsession with accuracy and sampling, which is one of the things that I also share to some extent. And this is something that's sometimes basically neglected and overlooked, unfortunately, in our community. So today he's going to talk to us about predictions of vapor-liquid equilibria of modern 3- and 4-site water models. Jeff's group also does a lot of code development. They are developing this open source code, if I'm not mistaken, for Monte Carlo called GOMC, and they also have a Python Python basically package for doing a hybrid Monte Carlo, a combined molecular dynamics and Monte Carlo. Our second speaker is Dr. Subha Chaudhuri. Subha did his PhD at Yale with Victor Batista at chemistry here, and that's one of the reasons that I know him. After finishing his PhD, he moved to Northwestern University. He's working with Professor George Schacht's group, and his area of expertise is basically using first principle simulations to calculate things like charge transfer, et cetera, et cetera. And today he's going to talk about predicting charge transfer rates. And the title is Marcus is good, but can we do better? And I have no idea who Marcus is, but I'm very curious to hear because this is not something that I have expertise in. So we're going to have another STMS next week. And our speakers will be Professor Betul Uraljan from Boğaziçi University and Dr. Nitant Gupta from University of Delaware. And I'm going to send you the link sometimes during the weekend. So with this, I would stop, and without further ado, I will leave the floor to Jeff. So Jeff, the floor is yours.
Okay, thank you. Okay, here we go, screen share. Okay, let's see, I'm gonna move people around so I can see my slides. Okay, so I assume, Amir, you can see my slides, everything's good?
Yes, everything is great.
Okay, all right. So thank you for having me. This is really a big thrill. So let's see, hopefully my computer will be, oh, there we go. Okay, so as Amir mentioned, you know, we do a lot of software development and we have a number of packages we develop. So we have the GOMC, which is our Monte Carlo simulation engine. We've been working on this for about 13 years now. We also are collaborating with Peter Cummings' group. It's actually a big collaborative effort between a number of different labs on this piece of software called MozDef. So MozDef allows you to build input to simulation engines, and I'll be using that in this talk. We also work with NAMD, and I think one of my big level ups was figuring out how to get NAMD compiled, because a lot of the calculations I'm going to show today were actually with a special version of NAMD. And we also have this program PyMCMD, which links GOMC and NAMD together to enable hybrid Monte Carlo molecular dynamics simulations. So we do a lot of software development, we do a lot of model development, and we have some applications things that we do, but I really love software and models. So that's what I'm talking about today. And I'm going to talk about a topic I avoided for 25 years. I did my very best to stay out of the water business. You know, I developed alkane force fields and sulfur dioxide and alcohols, all kinds of models, but never water, because water is kind of a scary place in the force field community. but anyway, I've been working on some projects, and this is actually my summer pet project, so it's a little bit of a work in progress. But I was reviewing water models. There's a lot of them, and there are some newer models that have come out using more advanced optimization techniques. We have the OPC, OPC3, GOPAL water models, and the basically the phase equilibrium predictions for those models are unknown, so they haven't been done yet. Some of these models even claim to be at the accuracy limit of what you can do with a 3 or a 4 site water model. So I think that's a pretty big claim to say that you're at the accuracy limit, but let's find out. So again, the force fields that we're going to look at here are your standard Lennard-Jones plus point charge, or maybe an exponential 6 potential. And so you say, geez, like why in, like 2023 are we, still doing these kind of small, simple models for water? And the answer is pretty simple, actually. If you want to simulate big systems, you need a model that's fast. If you want to simulate small systems, but the high precision, you need a fast model. So, of course, we have MBPOL, which has beautiful, predictive capability, but it's an extraordinarily expensive model to calculate. So, for example, you're not going to be simulating a 2 billion atom system using MBPOL. So we're stuck with these kind of, really simple models. So in the 3-site model, to quote Bono, you have basically 3 parameters in the truth, right? So you just have, that's all you've got. And maybe you have a 4-site model like the TIP4P style. And if you go to exponential 6, you can gain an additional parameter, but that's it. Again, the benefit is these are really fast, and you can get great sampling with them most of the time. I'll talk about sampling in a minute. And so these are the references, these are the models I'm pulling from, and these are the things I will be talking about today. These are just some of the parameters, so you could take a quick look and what you recognize when you look at these models. And I have split them. Let's see if I have. So I have split them into the top 3 models are 4-site models, TIP4P style, where we basically drop the charges from our oxygen atoms, so we displace them slightly. And then the bottom 3 are 3-site models, either based on a Lennard-Jones or an exponential 6 potential. This machine learned, so ML TIP3P is a re-optimization of the TIP3P style force field. And that one's interesting. I'll talk about some of these different issues. This one has Lennard-Jones sites on the hydrogen atoms. And I'll talk about whether that's really necessary or not. But again, you see kind of what you see with these parameters is they kind of cluster in certain regions of space. In terms of the epsilons and sigmas, you see the sigma for oxygen does not change a whole lot. Charges do change quite a bit depending on the style of model. And again, we have one of the things that's happened in the more modern water models is that authors have decided to treat bond lengths and bond angles as a free parameter. So instead of retaining the actual geometry of water, they treat that as a variable. And so that gives them some additional degrees of freedom to work with. Let's see, computer. Okay. All of the work, I'll just put a quick plug in for my former postdoc, Brad Crawford. So Brad developed this package called MOSDEF GOMC. It allows you to basically integrate a workflow. You can develop these integrated workflows with SIGNAC, and you can create kind of like a very simplified build process for all of the input files to GOMC as well as NAMD. And you can integrate that with SIGNAC so that now you can run hundreds, thousands of simulations from a single Python script, and it's fairly straightforward to do. So simple, even I can do it. So and I know just enough Python to be dangerous. So you know, anyway, it's a great package. You should check it out if you're interested in running Monte Carlo simulations. It also enables reproducibility, so reproducible simulations. So if I give you my workflow, you can get exactly the same answers as I produced today in this talk. So there won't be any, you know, well, what was your, you know, Leonard-Jones cutoff? What was your tail correction? How did you build the system? You know, everything is self-contained. So it's really great for reproducibility. Okay, so Amir mentioned sampling. Yes, sampling is important. It's important to check to make sure that we get good sampling. We can easily be fooled in simulations to think that we have good sampling and we do not. And this was an issue I ran into with running some of these simulations, that at very low temperatures, so 250 Kelvin, okay, it's subcooled liquid. And if you run Monte Carlo simulations for some of the foresight models, so some of the foresight models are a little tricky because the charges are large. And so this is a trajectory on the right. This is 100 million Monte Carlo steps started after a 50 million step equilibration. And what you can see from this figure on the right is that my simulation still looks like it's going somewhere. So the thing is, it's not going somewhere. It's just got very long undulations in the fluctuations. So it's taking the system a very long time to move from state to state. What this means is you need extraordinarily long simulations, or you need to run a lot of them to compile appropriate statistical averages. So this is where you can really get into trouble with Monte Carlo, and you kind of have to be on the lookout for it. And again, it will look like you have a converged solution, but really you do not. So what we do to combat this is that at low temperatures, you need to take into account collective motion of the water molecules. So we, in the Monte Carlo code, we have a multi-particle move. So this allows us to move all of the molecules at the same time, similar to a molecular dynamics time step. The other alternative is to run hybrid and Monte Carlo molecular dynamics simulations. And you may ask, if you're doing a constant pressure simulation, why not just do molecular dynamics? So that's a reasonable thing to do. In this case, what I'm going to show in some data coming up is I need to validate my data, my implementation of the models. So I need to validate them in GOMC because I'm going to use it to Gibbs ensemble. And so we use a hybrid method. Okay, so again, I mentioned this multi-particle move. We have the ability to do these. It's a force bias Monte Carlo step. So we predict the new locations of molecules by using the force. That introduces a bias. We have to divide the bias out. But in essence, what we're doing is we are rotating all the molecules at once or displacing them. And that gives us, again, the ability to sample collective motion of the molecules. So for these data that I'm going to present, though, actually, I'm going to compare kind of that multi-particle move with the hybrid. This is our PyMCND program, which basically integrates GOMC and NAMD. These simulations that I'm going to show, we run for 40,000 cycles, which is in essence, it's a 4 picosecond MD simulation followed by 20 Monte Carlo steps, and that makes up a cycle. And in the Monte Carlo steps, all we're doing is volume exchanges or volume transfers. So we're not doing any translations or rotations. We're taking care of that in the MD time step. All of the models we're using use an 8 to 9 angstrom cutoff with an analytical tail correction, and we're using typical Ewald-Salmer particle mesh. And what we found, when you compare different codes, of course, you put the same configuration into different codes, you get different answers, right? You get slightly different numerical answers for the energy. So what we found with GOMC and NAMD is that we have accuracy to 1 to the -3, 1 to the -4% relative error. So it's a very small relative error, and we found that statistically we cannot see a difference between that and an all Monte Carlo or all molecular dynamics simulation. So Looking at autocorrelation function, just to give you an idea of the difference in performance. So the hybrid method we ran, so this is autocorrelation function for basically this minus beta U plus beta PV, because that's the relevant quantity in a constant pressure simulation. And so looking at autocorrelation function, the black line is our hybrid method. And of course, this converges very fast. Standard Monte Carlo without multi-particle moves, just standard Monte Carlo with it using 2% volume moves, you see has much longer, basically the autocorrelate. So it takes much longer to generate uncorrelated samples. And that's what gets us into trouble. And this is even running on the GPU. So it's not a totally fair comparison, because the hybrid method we just ran on 4 CPUs for the same computer. In a straight Monte Carlo, we're actually also using the GPU. So so big difference in computational performance, at least under these conditions. So this is at 250 Kelvin, 1 bar. So it's a pretty tough test of the sampling. This is what happens. So this is what I'm talking about. If you, if you're looking at, so if you're looking at sampling and you're saying, I ran my simulation and standard deviation is pretty low, I think I've got a reliable average. So if we generate histograms of the densities that we observe in the simulation, and this is again constant pressure NPT simulation. So we've got the hybrid method. That's our kind of red area, and we have our Monte Carlo simulation. It's doing 5% volume movement, 2% multi-particle. Those two histograms match up. So those sit on top of each other. They're statistically indistinguishable within the error of my calculation. However, if I'm doing straight Monte Carlo, what we see, at least now, this is 100 million step Monte Carlo simulation. We see a shift in that distribution. So it's a very subtle shift, but it results in about a 0.5% error. So it's something to be aware of. It will make you crazy if you're trying to get converged results. You're trying to match data in the literature. This is why you're not, because of these low temperatures, you're not getting sampling out of standard Monte Carlo. So these data were all run with the hybrid method. So we wanted to show that we've done proper implementation of the methods or of the models before I talk about their phase behavior. And so we've got the OPC, OPC3, GOPAL, and TIP4P 2005. The GOPAL model, I did not have access to, to Michael Schertz's data yet. I asked, hopefully I'll get it. But their model is so good that comparing to experiment is almost as good as comparing to their original data. So we've got, if you see, you look at the literature data and you look at our work for OPC, OPC3, I mean, our models are basically our data are sitting right on top of each other. So we can be confident that we have a appropriate implementation of their model. And, for TIP4P 2005, again, the TIP4P 2005 data are now 17 years old, I think, 17 or 18 years old. So any differences, small differences we see are probably statistical sampling. You see that there's a little wag in some of their data. If they were to run these data again today, I'm sure that they would, we would be matching up. So anyway, so these are the data. I hope I've convinced everybody that we've implemented the models faithfully. So now when we predict things, that we can think about the predictions as being true predictions. In terms of VLE calculations, we're going to predict saturation properties from 300K up to 625. Again, that's because this is a work in progress, and running calculation below 300K is going to require some special sampling, and I haven't had time to set that up yet. We're doing Gibbs Ensemble. We're using GOMC. For those of you that are not familiar with Gibbs Ensemble, it's basically a 2-box simulation. We move molecules independently in both boxes. We do volume exchanges between boxes to achieve mechanical equilibrium. and we swap molecules between boxes to achieve equilibration of the chemical potential. Again, this is all done in GOMC. It runs on multi-core CPU, runs on GPUs and whatnot. We do a 50 million step equilibration. We do 100 million step production run. These are the kind of the distribution of moves. We also do multi-particle moves, small number of multi-particle moves, because we found that doing the multi-particle move, even though it is, I mean, our implementation is fairly slow, relative to, say, molecular dynamics, that the multi-particle move does help stabilize the Gibbs ensemble simulation and equilibrate faster. Again, we're using the same Lennard-Jones cutoff, analytical tail corrections, and things like that. And yeah, so 1,000 molecules. So we have pretty good performance in terms of finite size effects up to, within 25K of the critical point. Okay, let's see, what do we got? So I also do want to briefly mention configurational bias. So, and again, this comes up a lot, especially because now there are a number of hybrid Monte Carlo molecular dynamics implementations to do grand canonical. And at room temperature, so like say 300K, 298K, and at typical water density of 1 gram per centimeter cube, if you're doing unbiased trials, so if you're just throwing water molecules in there and hoping to accept them, you only accept about 1 in 10,000. And what that does is that it does not allow you to properly converge a solution. So, that approach basically isn't going to work. And so, or it's not going to work well. How about that? All right. So what we do for water, we do configurational bias. So just kind of a quick overview is we're sampling many locations. So we start with the oxygen atom. So, so basically we're using the Seatman group protocol for the most efficient way to insert water. And we try multiple, random locations, pick the best one. Then we pick the best orientation. We accept or reject based on the appropriate statistical probability. And because there's a bias, because we pick the winner, we divide out that bias. That's the algorithm in a nutshell. What I'm showing here on the right is kind of the performance of the move. And so in essence, what you see is that if you're only doing one trial, you basically don't get any accepted moves. And as you go, to more and more trials, eventually you hit a plateau where, no more trials will get you any more accepted, moves. But you can see you can get a substantial difference. So a factor of 10, well, if you have 0, well, 0 is a small number. So, but anyway, so that helps a lot. And it's system size dependent. So if you're running a 30K atom system, okay, we have the bottom. If you have a 300K atom system, you can keep, that's a big system. So you can keep adding trials to improve the performance of your swap move. And again, we've got CPU and GPU. Obviously, things are much faster on the GPU than the CPU, but that's that. So we're using, advanced sampling techniques to make this work. In the interest of time, I think I've got it. Well, okay. So this is just another example. It highlights if you use configurational bias, you're basically going to have, in this case, we had 1,000x better performance. This is a graphite slit pore simulation. So we're sampling. We're basically trying to fill up the middle region by doing an intra-box swap move. And so the blue and the black curve are each region if we're doing configurational bias. And if we're just doing this with an unbiased trial, that's the red in the orange curve. So it takes a lot longer to do that. Anyway, okay, here we go. Phase behavior. So this is the phase behavior predicted for each of these models. This is mostly new data. TIP4P 2005, those data are known. But GOPAL is brand new. GOPAL paper actually just came out in Chem Archives this summer. So GOPAL I ran, that's the first phase diagram for it. OPC3, this is also new data. Borrowed Jeff Errington's exponential 6 data. And so this is the phase behavior we get. So the interesting thing to note the GOPAL model's performance in terms of liquid density is rather impressive. These other models, OPC, OPC3, you know, so actually, you know, it's kind of a toss up is OPC3. So it's a 3-site model actually giving better, you know, saturated liquid densities than OPC. And also comparing to the exponential 6 model. So moving to the gas side, the exponential 6 model is actually rather extraordinary. And this is now over 20-year-old model. So this exponential 6 model of Jeff Errington was parameterized specifically for vapor liquid coexistence calculations. Its saturated liquid density prediction is about double the error of the other models, but the vapor pressure prediction is extraordinarily good compared to any other model in the literature. And again, I'll talk about why vapor pressure is important, why vapor density is important in a little bit. So this is vapor pressure prediction. Again, this is this violet curve. That's Jeff Errington's model. And okay, so then, you know, you see it's basically way outperforming everybody else. And all the other models are just kind of like, okay, they're different versions of not good. So, you know, that's kind of the state of water models, actually. It's very hard to get the vapor pressure of water right. And they're, you know, again, Jeff Errington's model is like the only model that's ever come close to reproducing the vapor pressure of water. We can do heat of vaporization. In the interest of time, I'm going to kind of move forward. Looking at critical properties. So again, we've got TIP 4P 2005 and the exponential 6 model. Very good reproduction of the critical temperature. All the other models are over predicting the critical point of water. Some substantially. The 4-site OPC model is predicting a critical temperature of over 700 Kelvin. In terms of critical density, again, every model is under predicting the critical density, and that's due to the issues with, you know, you notice the vapor densities are way too low. That's going to pull the critical density lower also. Briefly, I'll talk about this new model, machine learning TIP 3P. It's actually not that new. It came out in 2019. This is Pudge, by the way, in case anybody wants to know who the cat is. And why does Pudge have a frowny face? Well, I had to reverse engineer the model. The parameters are in the literature, but the Leonard-Jones cutoffs and tail corrections are not. So I ran a variety of versions of TIP 3P or the ML TIP 3P model. Some without hydrogen parameters, some with long corrections, with long range corrections, and some without. And so there are a couple combinations that do produce very good reproduction of saturated liquid densities up until about 350K. Below 350K, the performance declines substantially. So that's kind of this is, again, machine learning, new optimization of a 3-site water model, and that's kind of what you get. Looking at vapor pressure, again, same kind of situation with the various versions of ML TIP 3P, you know, all significantly under predicting the vapor pressure of water. Just to kind of summarize, if we look at the errors in different properties. So this is the mean absolute percent error. So basically I calculated the error with respect to experimental data and then, you know, plotted it up. So we have the different models here, and you see for liquid density, we've got a cluster of 4 models that are, you know, similar. So this TIP 4P is actually TIP 4P 2005. So you have the GOPAL model, TIP 4P, the ML TIP 3P. Those are all pretty good. And then if we look at things like vapor density, you know, the errors in vapor density are extremely large, so over 40% for most of the models, except the Jeff Errington model. So the exponential 6 model is, you know, under 10% error, and that corresponds to, you know, a very good reproduction of the vapor pressure. So these large errors in density directly impact the quality of prediction of the vapor pressure. We can dig into the density a little bit more. So it's instructive to look at the liquid density error as a function of temperature. So I put the 4 best models on this plot. The interesting thing to see, the GOPAL model has very, very good predictive capability over a wide range of temperatures. So 300 to 450 K. This is, and if you go up to 500 K, so this is under 1% error over a 200 K region of parameter space. I mean, this, and it's very well behaved. So it's very, you know, flat in that region. Of course, near the critical point, because the model overpredicts the critical point of water, it does have problems in the critical region. We have tip 4P 2005, also very good. Error is a little bit larger. And then, you know, you have the OPC3 model. Again, you kind of see what's happening is very, you know, it's a linear climb in terms of error. And then this machine learned tip 3P is very interesting. So it has a flat region between 450 and 550 K. You might even include this 400 K data point. But then it has, the error just takes off at low temperatures. So it's kind of a, I mean, my personal opinion is badly behaved. And I think this is kind of one of the dangers of machine learning, not knocking machine learning. Machine learning is great, but machine learning also needs to be guided by expert knowledge of the behavior we want the models to provide us. So anyway, let's see. So why do we care about vapor pressure? Just quickly, we care about vapor pressure because vapor pressure has something to do with the range of interactions of the potential model. And so this is some work I did with me potentials a long time ago. But in essence, what we showed is that by altering the shape and the range of the potential, we alter the eccentric factor. So we alter kind of the slope of the vapor pressure curve. So if your model isn't getting vapor pressure right, there's some fundamental physics it's also not getting right, which I guess, you know, I think we all understand and appreciate, but we can directly correlate it with some measurable physical properties. So in summary, so sorry, I'm a little over, but in summary, we've got, you know, the Errington model is the best reproduction of critical temperature and vapor pressure. Tip 4P 2005 is a really very good all around. It's kind of one of my favorite water models. The GOPAL model is, I think, to me, really extraordinary reproduction of liquid densities. If you look at Michael Schertz's paper, it's like a super tuned tip 4P. Its performance in liquid density is really, really good. It's just got this flaw in the near critical region. And then, you know, we've got this machine learned tip 3P. It reproduces some parts of the phase diagram well, others not so well. More summary, what can we learn about a new model? Let's say we wanted to make a new model. So if we fit only the density and heat of vaporization at 1 bar, you're not going to get reliable vapor-liquid coexistence. However, what we see from the Schertz model, so that's the GOPAL force field, what we see is that if you fit over a broad enough parameter space, it's remarkably good at VLE predictions with never having done a VLA calculation. So that provides us some insights as to how perhaps we might apply machine learning and high throughput simulations to optimize models for vapor-liquid coexistence without ever having to do vapor-liquid coexistence calculation until the very end. And then, you know, improving vapor pressures, you're gonna have to use some gas phase data. We don't know how that's going to affect your liquid density predictions in your liquid properties, but we have some insights from all of these models combined. If you look at the Errington work, it'll probably make the liquid density slightly worse. The question is how worse, and you know what can we work with there. Finally, some acknowledgments, and again, NSF for funding. Big shout out to Brad Crawford, who's currently at Georgia Tech. He is the developer of PyMCMD and Mazda GoMC. So he's made a lot of magic happen thanks to his efforts. And then also long time, PhD student and longtime collaborator Mohammed Farhagi led a lot of GOMC development, and we've got Yunus Nahaji, Greg Schwing, and my longtime collaborator and friend Lauren Schwiebert, all in computer science, who did a lot of the work with the GOMC development and the multi-particle movement optimization, and my my graduate student Maxim, who helped out with some of the force field validation. And that's it. That's what I got. So apologies, I'm slightly over, but hopefully not too over.
Thanks, Jeff. I mean, you're on time, I mean, for what you're considering. And thanks a lot for the wonderful talk. So let's give Jeff a round of applause, and then we can move on to questions. So while people are thinking about questions, I'm just going to read a question that is on the chat by Akash Kumar. Let me see whether the name is Bal. How do you choose the number of water molecules in multi-particle MC to minimize fluctuations?
So we move all the molecules at the same time. So we're not choosing a subset. We're just saying every molecule you're moving, just like MD.
Okay. So we have Woody. Woody, go ahead.
Thank you, Dr. Amir. Hi, Professor Potoff. Thank you so much for the presentation. This was very, very interesting. I enjoyed this. I had a couple of questions. So the first one, I think, is a follow-up to the last question. So for the multi-particle move, what does your acceptance rule for that look like? Is it just a difference in the Boltzmann weights after you finish updating your coordinates, or what all goes into that?
Okay. So the acceptance rule is so unpleasant. I'll have to shoot me an email. I'll send you the paper.
Okay.
In essence, what we've got to do is, I mean, it's full of like hyperbolic sines and cosines. It's like what we have to do is we're calculating the force. We're using that to determine the new location of the part of all the molecules. So we're doing force bias. So because we've basically cheated by using force bias to move the molecules, now we got to divide out all of the bias we introduced with the forces.
Right.
So it is pretty complicated, but there are a couple papers on this, so I'd be happy to just send you one of them, because we did not invent the multi-particle move by any means. What am I'm trying to think. There's something on my mind of multi-particle. The issue is, like, you could imagine if you just tried to randomly move all the molecules without a force bias, you would never accept any of them.
Right, yeah.
So that's why we have the force bias.
Okay. Okay, awesome. Thank you. But yeah, yes, please. I'd love to see some of those papers.
Okay.
And I had one other question. So for the Leonard-Jones cutoffs, 8 to 9, that feels a little bit small compared to some of the older water models. Is that just what these different water models were fitted to, or?
Yes, in fact, actually, even the ML tip 3P model, I found out that they allegedly, I'm going back and forth on this one, but allegedly they use a 7.5 angstrom cutoff. So what I did in all these calculations is I did my best to be reproducible to whatever they said in the paper.
Right.
So like tip 3P or tip 4P 2005, the cutoff is 8.5 angstrom. And in the GOPAL paper, it's 9 angstrom. So they are very short cutoffs. When you add the tail correction, everything just kind of it all kind of works out. So, that's kind of, anyway, so all the data I've shown you can see from the liquid densities I presented are me doing exactly whatever they said in the paper. So, but I agree, like 8 or 9 angstrom kind of makes me a little nervous.
Right, yeah. But yeah, thank you so much. Very awesome work. Thank you.
We have Baron. Baron, go
Hi.
ahead.
All right. So thank you for the nice talk. It's nice to see you again. I just wanted to ask so you're doing Monte Carlo with force bias moves, and I just wanted to know if you could briefly summarize some of the pros and cons of that approach versus a more traditional, like a hybrid Monte Carlo molecular dynamics, where the molecular dynamics just runs the short trajectory and then you accept or reject?
Sure. So I'm a big fan of the hybrid method. Even though I can tell you, we spent tremendous effort putting the multi-particle move in GOMC. Here's the pro of the multi-particle method. It's in GOMC, so I just run one piece of code and it kind of does stuff. The con is that, you know, it's not as fast. Like, performance is the big issue is computational performance. So that's why the liquid densities I showed originally, those were all done with a hybrid method. So the computational performance of our hybrid MCMD implementation is substantially better than our multi-particle implementation in GOMC. It is a very challenging computational problem. We're actually, in the multi-particle move, we're actually doing, I think, more work than you're doing in a molecular dynamics time step, because we're calculating the energy and the force and the acceptance criteria. And I'll be honest, you know, we don't have the professional programmers that GROMACS and NAMD and Amber and those groups have. And there's a lot of magic in those codes that make them fly. And so, you know, if we had some of that magic, I mean, we would be doing a lot better. But I think that's really, it all comes down to, you know, in terms of, okay, in terms of, can I get equivalent quality data out of both methods? Absolutely. In terms of how long it takes me to get it, hybrid MCMD, I'll get it way faster. If I have to do, you know, if I have to do a lot of multi-particle moves, 1 or 2%, it's not too bad. If I had to do 50% multi-particle moves, I'm not even going to think about it. So anyway, I hope that answers your question. I don't mean to like dog my own software, but
yeah.
But yeah, it's primarily a computational issue.
No, thank you.
So I actually have 2 questions. One follow-up to Baron's question. The other one is my own question. So my first question is regarding implementing multi-particle move. Because one of the big advantages that I can imagine is parallelizability, right? That compared to regular Monte Carlo, you can now basically parallelize force and energy calculation fairly easily, which is also obviously done in hybrid Monte Carlo as well. My question was whether you have tried to relegate that force and energy calculation part to a code like LAMS that basically allows you to use its library, like to have like access to a trajectory real time. So you basically communicate back and forth with LAMS. It calculates the forces, you calculate the acceptance criteria, and then you do it over and over again, right, when you need it.
So we have not done that. You know, we have, you know, the multi-particles on GPU. We spent a lot of time trying to optimize its performance on the GPU. And it's, you know, the GPU version of it in GOMC is substantially faster than what's on the CPU. So we haven't tried the LAMPS approach. We could. The other approach we're looking at is to borrow some code from OpenMM. And, you know, these are things that, that we are looking at, but there's a lot of, I have to say, there's a lot of buried labor involved in some of these things that I can't, you know what I mean? Like, it's,
yeah,
you spend a lot of time on that. It doesn't produce a paper, right?
I know that as a programmer, so I completely understand what you're talking about. So,
which I would love to do, but students want papers. So,
yeah.
Anyway, so yeah, but all you know, good options. You know, I mean, this is originally when we put multi-particle in, the thought was that we would, because you can parallelize it, that if we were doing polarizable force fields, this is to support eventually doing Drude oscillator and things like that. Because if you do Monte Carlo on Drude oscillator without a multi-particle move, you got to reconverge all of the energies anyway, and
Yes.
you're just going to get killed. So
Exactly.
you need that. That's kind of the foundation. So we've got it in there. So hopefully, sometime in the future, not too distant future, we'll have support for Drude oscillator. So these are just some kind of backstory on that.
And I have now I have a question about ML3P.
Yes.
It was a bit suspicious to me that you have this perfect match in density in a region, a particular region in temperature, space, and then we had big deviations everywhere else. Is it because where they got their training set for like the machine learning? What was their general procedure for basically creating this model?
Well, it's okay. So it's a little opaque. So the paper talks about kind of using a hierarchical, genetic algorithm. They're using different data sets to kind of refine the model. I've had some discussions with them, and let's just say that there's still some things that are not clear. I mean, to me, my take on this is that they, you have an automated algorithm. It optimizes parameters, and the objective function forced it to what it is, and without kind of the human intervention of saying, like, is that what I want?
Yeah.
Right? Because we've run into this before too, when we've done particle swarm optimization, where we just have totally unsupervised, it's giving us parameters. And, you have to give it the appropriate guardrails to tell it, what you really want, not what it thinks you want. So I think that's kind of what happened, because I do think that what we see this with other models with vapor pressure. So even if you do something simple, let's say I want to do ethane, and my objective function says I want to optimize the vapor pressure of ethane equally well as the liquid density, it'll actually push you to have worse liquid densities because it's just that weight is pushing the algorithm. So I think it's all in the optimization in the objective function and how you weight the quality or the importance of various quantities in that. And I think that's where they got, how they ended up where they ended up. So
makes sense. Thanks a lot. So let's applaud our speaker, Professor Potoff, one more time. And in the interest of time, we move on to Subha, our next speaker. So Subha, the floor is yours.
Sure, thanks, Amir. Give me a second. Let me share the screen again. Okay, so hopefully everyone can see the screen all right. Yeah. All right. Then thanks again, Amir, for both the invite and the introduction up front. I am Shubho. I'm a postdoc at Northwestern University in the Department of Chemistry. And well, Amir, I guess already guessed that I will be in the job market in the coming year. So maybe some of you will hear back from me in a few months. But today I'm going to talk about predicting charge transfer rates. I have in my title this thing, Marcus is good, can we do better? Now Marcus is this guy, Rudy Marcus at Caltech. In fact, he turns 100 today. And he is a Nobel laureate who got the Nobel Prize in chemistry for his work on predicting charge transfer rates. Now, how do we look at electron transfer? So let's say we can think of it as a donor-acceptor system, and we can have an electron that moves from the donor side to the acceptor side. There is very complicated multidimensional potential energy surfaces involved when you're basically hopping from, let's say, some minimum energy point of your initial state that, let's say, I'm calling I, to some final state that we're calling F. In my case, because we are looking at some reaction which involves charge transfer, so these I and F, there is a whole distinguishing feature between whether or not you want to think of these as adiabatic states or non-adiabatic states in terms of the fact that whether you're allowing crossings of surfaces to happen or whether you're having avoided crossings. But the framework that I'm going to talk about, that does not really involve caring all that much about it. So the way it works is we have your initial and your final state, and let's say you want to go from there to there. You can come up with some reaction coordinate for it, and then think of it as, oh, the minimum energy of this is when the electron density was localized on the donor, and in the other case, the final state, it was on the acceptor. Now you can have an activation energy for this, so regular transition state theory type things. And the way things work is, as the activation energy increases, you'll expect the rate of charge transfer to decrease, which is understandable because there's a higher barrier to this process. And this can be described by very standard, let's say, Arrhenius type equation. Now, the trick is a lot of the charge transfer modeling that was done previously, or also done in a lot of studies that I see even now, is overly simplistic, in the sense that the way things are seen is there is a donor and there is an acceptor part, and there is a charge that moves from the donor to the acceptor part. Now, that is probably not all that's happening. In reality, quite often all of these experiments are done in solvents, where as the charge is moving, not only do we need to change the configuration of the molecule or the system in general, but all of the solvents, depending on how polarizable they are, they need to reorganize to accommodate for the new distribution of charge. So that's something that Marcus theory incorporates in it. And the way it works is, let's say you have something called delta G, which is your standard Gibbs free energy, which is the difference between, let's say, the two minimum energy points, and what we were calling activation energy. I'm now denoting it as delta G dagger. Now, as you look at these two parabolas, right, as the delta G increases, that is, as we are moving the final states down below, what you expect to happen is that the rate will go up. Once again, nothing new up to this point. But as you keep increasing the delta G, if you look at the previous equation, the rate should continue to go up. But the problem is that actually what we care about is not the delta G, but the delta G dagger. So if you keep increasing the free energy of the reaction indefinitely, as it turns out, unlike what we used to think previously, the rate does not keep increasing continuously, nor does it saturate at some point. It will actually go down, because now there is a barrier still to go from one parabola to another, but this intersection is happening on the other side. So this is something that Marcus was the first person to predict. And you can run through a whole bunch of math. At the end of the day, these are just simply displaced harmonic oscillators. And this is the functional form of the Marcus theory. And there are these two regions that are defined as normal region and inverted region. So normal is when you would expect your normal behavior of, as you increase delta G in magnitude, or rather, let's say, decrease delta G, the lower you're going in energy, the rate keeps going up. And then there's the inverted region, where you're getting an inverted behavior of the behavior that was expected. And there were experiments done on it. And finally, this inverted region was seen experimentally, which eventually led to Rudolf Marcus getting the Nobel Prize. One thing that I will ask you to note is that in the equation here, if you look at the equation, if you are plotting delta G versus your KET, which is your electron transfer rate, this should be a symmetric parabola. But when the experiments were done, the parabola, as it turned out, is asymmetric. But still, no one massively cared about it, because this was the first time the inverted region was demonstrated, and that was already a very, very big deal. So this eventually led to Marcus getting the Nobel Prize. What people did back then, so these are these famous Claus and Miller experiments, is they just introduced some fudge factors that you can see here. There is this frequency of around 1500 wave numbers that they introduced, and they roughly said that, okay, your lambda S, which is the reorganization energy of the solvent, should be around 0.75 eV. Your lambda V, which is your internal reorganization energy of the molecule itself, should be around 0.4-ish eV. So all of these are fitting parameters up to this point. Now we decided that, okay, as we are slowly moving towards more and more data-driven things, it would be nice to be able to predict all of these things without having any fudge factors. So all that we want to do is, okay, you give me a chem draw of a molecule or of a system, and just from that, I should be able to give you how fast an electron can move from one side to the other. So we started off with this thing where now we saw that, okay, what happens when we localize the electron on one side of a molecule versus another one? And then depending on how the electron is localized, we can fragment our system to define what is called a donor and what is called an acceptor. And we can form these parabolas once again. All of these are energies that can be computed fairly easily with electronic structure theory, one flavor of which is DFT, or density functional theory. So we calculated the delta G of the reaction accordingly. These are just, we minimize the two structures in a way where the electron is first localized on the reactant and in another case on the product. The donor and the acceptor, and we are calling those two states reactant and product states. So when we compare the delta G with in this correlation plot with the experiment and the calculated ones, as you can see that we have excellent correlation between the calculated and the experimentally observed delta Gs. And this is fairly robust. We have used a whole bunch of different DFT methods, and across the board, we get fairly good agreement. So far, so good. Next, we thought, okay, let's try and do a lambda calculation, which is the reorganization energy. This tends to be a little bit tricky. Once again, I'm going through a lot of material. I'm not doing a lot of these justice because each slide in itself is probably a 15-20 minute thing. But anyone who's interested to learn more about these things, please reach out to me or ask me any questions at the end of the talk. I'll be happy to answer. So yeah, we can restrict the nuclear coordinates and only allow the electron to move, and also restrict the electron and only allow the nuclei to move. And based on that, we can move around on different potential energy surfaces of the reactant and product states and calculate how much energy is needed to reorganize from the reactant to the product state. And then there's something called electronic coupling, which essentially involves how much the molecular orbitals overlap in space and how the energies of the donor and acceptor states are aligned. So there are ways of computing these. Again, I'm avoiding a lot of math here. These are very hand-wavy explanations, but once again, these are parameters that we need and we know how to compute them. So based on these, we plugged these in the Marcus theory picture, and our rates were off by 4 or 5 orders of magnitude, which is not an acceptable margin of error in this field. Probably in astrophysics, but definitely not here. So we tried something called constrained DFT, where you can use a Lagrange multiplier, and instead of fragmenting the molecule, you can just restrict your states which you're accepting as a solution to your optimization process. But even that was not faring any better. So then what we decided that, okay, there is no particular reason why your optimized geometry or the minimum energy configuration should be the maximally coupled configuration. So this once again brings us to sampling of different configurations. Now, once again, because these are fairly big molecules by full quantum calculation standards, it's difficult to do full quantum dynamics or even semi-classical dynamics, where now we are not only looking at how nuclear coordinates evolve over time. You saw the previous talk, which was wonderful, and it briefly touched upon the fact that you need a lot of steps to eventually get enough sampling. Now, when you're thinking about charge transfer processes, electrons move way faster than nuclei do. So your steps need to be even smaller if you're doing quantum dynamics, else you'll completely miss charge transfer events happening. So that really makes it tricky to sample these things effectively. So we just decided to arbitrarily give like random dihedral angles, rotations and all, and generate a whole bunch of configurations, and from there just calculate energies at a quantum mechanical level and do things from there. So this improved things significantly to a point, and the electronic coupling values also seemed fairly robust. It was fairly independent of what DFT method we used. So we found that we were now within 2 or 3 orders of magnitude of the Marcus rates that were observed experimentally. But once again, we would want to do better. So we thought, what are we missing? Now, as it turns out, we have not taken into account molecular vibrations, which can be a big thing. Now, if you have certain types of vibrations which bring the donor and acceptor closer, that means you're increasing the spatial overlap of molecular orbitals in that process. And that means that something can click in the process and you can have a charge transfer event there. So we decided to design something like a single effective mode, and we repeated the Marcus energy, the Marcus theory electron transfer rate calculations. As you can see, we have incorporated a new term inside the Marcus rate expression, which involves this omega effective or some effective mode of vibration. And we now also have decided that, okay, we need to separate out our solvent and internal reorganization energies, because the solvent is not vibrating, the molecule is. And when we use a formalism like this and calculate reorganization energies back again, what we see is we were still a little bit off. So then we realized that, oh, because we have fragmented our system, in the real system, the donor and acceptor are bound together. But the system that we have defined, because we have fragmented, these are two infinitely separated species. So there is a larger solvent shell around both of these. So in order to account for these increased solvent shell effects, we had to do some fairly straightforward algebra there, and then come up with some ways of calculating the reorganization energy when the donor and acceptor were in their original configuration. And when we do that, it seems that our energies are in the ballpark of what the Marcus paper, the Klaus-Miller paper initially had predicted. So as you can see that your lambda S and lambda V are around 0.75, 0.45-ish, and what we are computing is around 0.5, 0.8-ish. So very, very much in the ballpark. Now, if we go back to calculating the charge transfer rates, we are doing significantly better in the normal region. In the inverted region, we are still a little bit off. So what we decided is, once again, let's figure out what is missing. We have oversimplified this whole vibrational thing in terms of restricting it to one effective vibration. There are all sorts of vibrations, and there will be a lot of overlap of these vibronic states. And as you can see that in the normal region, these overlaps are not as much, whereas in the inverted region, there's massive overlap. So that means that we can't really ignore these different vibrational states anymore. So we came up with this full expression. Shouldn't say we came up, this was existing. We did some modifications and some computational implementations of these. Now, it's difficult to compute things like this when you have a whole bunch of these nested sums and products, when you're doing this any grid-based summing or integrating procedure. So we took tricks from the stochastic methods community, where let's say you can try and find the area of a circle by just dropping points in there. So if you can sample things intelligently, because we know the functional form that this is supposed to take, we can do importance sampling and sample at areas where we think that there is larger contribution to this sum, and sample less at areas where there isn't. And we can come up with neat little tricks to implement some Monte Carlo methods to eventually get this sum done. Fairly good convergence. We would say that after 1 million Monte Carlo steps, we have pretty much converged to the rate that we wanted. And now if we go back, we see excellent agreement all across the board. Now I'm showing you in orange what is pretty much the standard practice in the community. And as we increase the complexity of the model, what can be achieved. So we can do fairly well. And as you can see, these are rates spanning from like 10 to the 3 all the way to up to 10 to the 10. So like 6-7 orders of magnitude. And these are multiple different complexes. And there has been no sort of fitting parameter, no fudge factor introduced. Everything is just computed ab initio first principles. So that gave us a lot of confidence. And as we found out that there are interesting things that come out of analysis of these things. So we took some sample molecules from the different areas of inverted region and normal region. And as you can see that in the normal region, if we decompose the rates, you can see that all of the modes here, irrespective of what frequency they are contributing a fair bit. And as we start moving towards the inverted region, if you squint, you might be able to see some darker red shades for the modes that are closer to 1500 wave numbers. But as we move to the inverted region, the maximum rate contributions come from these 1500 wave number modes, which comes naturally from all of these calculations and analysis. Whereas previously we showed that it had to be a fitting parameter in the experiments. So we can now predict a lot of things, bring a lot of physical insight from these models. And we know why certain frequencies are important and how to, maybe even without doing a lot of these calculations, completely predict what kind of frequencies will be of importance and give more importance to those. So in the interest of time, I won't go into a lot of detail about what can be done with frameworks like this, but we have already extended these out a fair bit. So what I showed was a single molecule. We can look at how, let's say, photoacids can do ultra-fast quenching through charge transfer processes. And this can be used to design photo switches. And for this, of course, we need to move to the excited state. That's a whole different can of worms that I'm not opening today. And if you have an electron being transferred to a solvent molecule, sometimes we need to introduce the solvent explicitly, and we can relegate the other solvent molecules to some dielectric continuum. Sometimes that's not enough. We can get very, very good agreement. This is something that was an open question for over 10 years. No one was being able to really understand why one naphthol had significantly fast photo quenching compared to 2 naphthol. So we were able to do that. All of this is out published now. And we can do full potential energy exploration. And if the system is simple enough, we can go even further, well, beyond Marcus, in the sense that we don't even need Marcus theory anymore. We can just do something like surface hopping, made famous by John Tully at Yale. We can look at how silver nanoparticles aggregate through charge transfer processes. Once again, same framework. We have taken different experiments now, and we are trying to model all these different experiments with similar frameworks. You can look at extended system. You can look at how charge transfer happens through proteins, through bacterial nanowires. You can move to the other side of the spectrum. Once again, look at very simple, let's say, ferrocyanide.
So, sorry, I don't want to interrupt, but we are already above the 20-minute mark. So
yes, I'm pretty much done now.
Okay.
Yeah. So yeah, these were all the different kinds of applications that can be done with frameworks like this. Once again, I'm not doing justice to any of these things because I've tried to include a lot of things in a very small period of time. All of these papers are now out. These are some references that you can look at if you want to know more about it. Once again, please feel free to reach out or ask me any questions. And you can do these things for single molecules, for extended systems, for periodic systems. We can look at spin transfer, we can look at energy transfer through similar types of models. And with all that, I'd like to acknowledge the different centers that I've worked for over the past few years, the different funding sources, and my PhD advisor, Victor Batista, my postdoc advisor, George Schatz. None of this would have been possible without the guidance of these wonderful people. And thank you to the STMS community for your time, and Amir and Sapna for the invitation. I understand it was very, very dense, but please feel free to ask any questions. I'll be happy to answer.
Thanks, Shubha, for the wonderful talk. So let's give Shubha a round of applause. We only have time for maybe a very quick, short question, if anybody has any questions. Okay, so I'll ask a very quick question, and then we can maybe conclude the event after that. So this more accurate method that you have developed, how much more expensive it is compared to traditional methods, right? In other words, how does it impact the throughput of these rate calculations?
Right. So in the Marcus rates that you're calculating, you only need to optimize the system. So once again, it depends on the molecule, how the potential energy surfaces look like. If the minimum is very shallow, then it is of course difficult to reach by standard optimization techniques. But for the methods that we are working on and we have developed, you also need to calculate the Hessians and look at the vibrational modes there. So it depends really on the number of electrons that you have in the system. So the bigger the system, it gets more and more expensive. But for the system sizes that I showed, it probably takes maybe a day and a half more to calculate, which once again by standards of electronic structure theories is not much. But as we have moved more and more towards more complicated systems, like the protein systems that I was showing on, that's work in collaboration with Nikhil Malvankar, who you might know, also at Yale. So for those, it's very difficult to calculate normal modes at a quantum mechanical level. That will just be intractable. So there are, of course, ways of getting vibrational modes from molecular dynamic simulations as well. So then we'll have to move more towards those things. All of this is very much work in progress, and a lot of the things that I want to develop over the coming years is based on frameworks like this, and hopefully with like more and more machine learning based methods, we'll be able to, let's say, initialize and predict Hessians and maybe minimize some error function and get to Hessian calculations faster. So we will see how those things are, but not that much expensive at the moment.
So let's thank both our speakers, and this is the end of the official part of STMS. We look forward to seeing all of you next week. You are, however, free to hang around if you want to talk to the speakers or catch up with your friends.